Thanks, Don. It's really great to be here, and it's exciting to see so many people learning all about the statistics of exoplanets and whether there are planets in our data. Today I'm going to show you a lot about surveys that hopefully will discover thousands of planets in the future. We'll begin with a timeline rather than an outline, because the whole structure of this talk is what has already happened, what is happening now, and what will happen in the future in terms of transiting exoplanet science. Beginning with the Kepler mission in 2009 to 2013, we'll then go to K2, then on to Tess, Cheops, and Plato. We're going to skip over James Webb, and then we'll end up with the Plato mission. This is going to take us to 2024, which might seem like a long way in the future, but that's actually only 8 years from today. So odds are in 2024, many people in this room will still be very actively engaged in astrophysics, and you'll be thinking about what to do next in the upcoming missions that Carl talked about this morning. To begin, we learned a lot about Kepler earlier this week. We know the mission operated from 2009 to 2013 and detected thousands of planets orbiting other stars. We're going to fast forward ahead now until May of 2014. And of course, as you know, things didn't go so well for Kepler in May 2014. The second of 4 reaction wheels failed, which could be seen as a bad thing. After all, Kepler was dead. But it was also the birth of the K2 mission. And in many ways, K2 has taught us a lot about exoplanets that would not have been possible if we'd continued along with the mainline Kepler mission. Looking at K2, the way the mission works is that if you look at the Kepler spacecraft, there's a ridgeline between the solar panels. And along that ridgeline, if you hit it just precisely with the light from the sun, you can actually cause the spacecraft to balance. So even though you no longer have 3 functional reaction wheels, you can use this solar radiation pressure as essentially a third reaction wheel to make sure that you're able to point stably at a particular part of the sky. The catch, though, is you can't just point anywhere you'd like. You have to point along the ecliptic plane. So here we have a figure showing how the K2 mission works. We have the sun here, and Kepler, of course, is in orbit around the sun, just like the Earth is. Kepler is trailing behind the Earth. And K2 is pointing in one particular part of the sky. It has to point in a certain direction so that there's sun on the solar panels, but not sun in the aperture of the telescope. And it's able to stare at that field of the sky for roughly 80 days. So we start off here, the spacecraft moves along, and we end up over here. And then at that point, we switch over to another field of view along the ecliptic. We've been doing this since 2014, and we've already collected data from numerous K2 campaigns. We're going to talk more later today about all the interesting science highlights that have come out of the K2 mission so far. Here's where K2 has been pointing. This figure here is showing the right ascension versus declination, and this black line here shows the ecliptic plane. If you ever look at the horoscope page in the newspaper, you'll recognize a bunch of these names. And of course, you're now going to be able to find planets in your own favorite constellation. So remember that for public outreach purposes. If someone asks you what their horoscope is, you can segue the conversation to K2 instead. Here, there are a bunch of different colored fields, and I want to point out that there are actually some fields coming up where you yourself can put in proposals for targets you'd like to look at. So if you're feeling like you have lots of free time on your hands, go ahead and write a director's discretionary proposal for campaign 12 or for campaign 13, or put together a full cycle 5 proposal to suggest targets for campaigns 14 through 16. And you can see where those are up here. And they're currently looking for targets for these blue fields 14, 15, and 16. What ways does K2 differ from the prime Kepler mission? Well, there's one obvious way. Kepler lasted for 4 years. K2 lasts for about 80 days per campaign. Another difference is that Kepler just looked at one particular region of the sky, whereas K2 is looking at numerous fields along the ecliptic plane. These K2 fields contain about 10,000 to 30,000 stars each, whereas Kepler looked at 200,000 stars for the full mission. By the end of the K2 mission, then, that means we're going to cover about the same number of stars, if not many more stars, than the original Kepler mission did. But the difference is that there's only a finite number of bright stars in any patch of the sky. So if Kepler were to stare at the same field for 30 years, it would never pick up more V of 11 stars, because there just aren't going to be new stars that magically appear in that field. With K2, though, we get new bright stars every single campaign. And that's great, because bright stars are best for follow-up observations and planet characterization. The targets for K2 are also selected in a pretty different manner than the original Kepler mission. In Kepler, the vast majority of targets came out of the Kepler science team. And then there was a guest observer program, but it wasn't where the bulk of the targets came from. With K2, the vast majority of targets come from guest observers, and those are primarily targets that are observed at 30-minute long cadence, but there are a handful of targets observed at 1 minute short cadence. For planet searching, all of the Kepler fields were searched for planets by the Kepler team, and they actually released a list of threshold crossing events and a list of Kepler objects of interest, those KOIs or KOIs, and a list of planet candidates with dispositions. The Kepler team also took on some of the responsibility for vetting these objects, figuring out which were false positives and which were real planets. K2 is a little bit more like the wild, wild west. We have a whole bunch of different collaborations with many individuals who've come up with their own K2 pipelines. Initially in K2, we just got the image. We didn't actually receive light curves from the Kepler team. Those pipelines came up with different ways to deal with disentangling stellar activity as instrumental systematics and planetary transits. Each of them have pluses and minuses, and there have been some interesting papers lately comparing the performances of these different pipelines and different data sets. And the underlying message seems to be, depending on what you're trying to do, there might be a particular pipeline that works better or worse for your purposes, but you can't guarantee that that individual pipeline will work best for all applications. Going forward now, the K2 Science Office is actually releasing light curves. So if you'd like to, you can use those light curves or any of the other publicly available light curves online. For finding planets, though, you still need to rely on the community. In terms of scientific emphasis, the main Kepler mission goal can be summed up in a single sentence. We want to figure out the frequency of Earth-like planets around Sun-like stars. For K2, there are numerous scientific goals, mostly because we're surveying different patches of the sky for different lengths of time. You can do exoplanet science, whether it's transits or microlensing, but you could also do things like astroseismology, which was also done during the main Kepler mission, or perhaps even try to study supernovae by looking at regions of the sky where you think supernovae are more likely to occur, and that would be out of the galactic plane towards other galaxies. So K2 has been looking at lots and lots of targets selected by the community, and I think one way to tell how the K2 targets differ from the Kepler targets is to look at these nice figures put together by Dan Huber. Here you can see an HR diagram, well, essentially, this is actually radius versus effective temperature, showing the distribution of Kepler target stars. Here in red is where most of the stars are concentrated, and that falls around stars like the sun. If we look at K2, though, you can see we now have 3 clumps of stars. There are those sun-like stars, there's some giant stars, and then there are also all these little guys down here. And that's because 41% of K2 targets are actually low-mass M and K dwarfs. The reason for this is that if you're only looking for 80 days, you're not going to see that many transits. So even if you have a planet that transits every 5 days, you want that transit to be deep enough so that once you phase-fold all your data, you can actually detect the planet with some significance. Smaller stars are smaller, so the transits of a planet of a given size are deeper, meaning you have higher signal-to-noise detections. You have to worry a bit about the brightness of the star, but on average, it's easier to find a planet around a low-mass star than it is around a high-mass star. The other advantage with these cool stars is that their habitable zones are closer in. So even though K2 only looks for 80 days, you actually are sensitive to potentially habitable planets. K2 has been remarkably productive. Here is a distribution showing the number of papers published from Kepler and K2 over time. So we're starting off here with about 400 here and 300 here. And you can see this is 2013, and this blue bar is all from Kepler. If we add on K2 in 2014, you can see this tiny little red sliver. Here in 2015, that sliver is growing. And in 2016, we've already published more papers now than we did in all of 2015. That's pretty impressive for K2. And if we extrapolate and assume that we're going to be just as productive for the rest of the year as we were for the start of the year, this gray bar shows just how many K2 and Kepler publications we expect to have by the time the year is over. So that's pretty exciting, but it means you might have some late nights reading AstroPH. There are many, many highlights from the K2 mission, and it's difficult to do the whole mission justice as part of a short talk. So I'm going to show you a couple highlights, but please don't be offended if your own favorite result isn't among this list. One of those highlights is that from Kepler, Roberto Sanchez-Ojeda and a couple other scientists found planets that were very close in and being tidally disrupted. That's continued with K2. We have this planet here, which is smaller than 2.5 Earth radii. We're not sure exactly how small, and in a 9-hour period. Here's the way the planet might actually look. If you have the star here, and the planet's there, it actually has a trailing tail and a leading tail. And when the planet crosses in front of the star, you see an interesting asymmetric transit morphology. That's pretty cool. Another interesting result that came out of K2 is that we now have additional evidence that hot Jupiters are not necessarily lonely. They do have friends, guys. And one of those Jupiters with friends is WASP-47. We've known about the hot Jupiter, WASP-47b, for a while. But now, thanks to K2, Juliet Becker and her collaborators found that it has 2 smaller planets. There's a super Earth here on a 0.8-day period, and another planet that's 3.6 Earth radii on a 9-day orbital period. That's exciting, and it suggests that as we continue to survey the sky and look at more of these radio velocity planets with transit surveys with high precision photometry, perhaps we'll find additional evidence of closely packed systems that also have hot Jupiters. Systems like this are difficult to explain with formation theories, so it's really going to help us advance our models of how planets form and evolve. Another cool K2 science highlight came out recently from Caltech. This was a paper by Trevor David and his collaborators, where they looked at this small star here. It's actually an M3, and it's very, very young. So even though it's only a third of the mass of the sun, it's actually larger than the sun in terms of radius, because it's still cooling. When they looked at the photometry, it looked a bit like this. You can see there's a lot of modulation here. But when they detrended it and got rid of the stellar variability for the purpose of planet searching, they saw this nice transit light curve. We now have a 6 Earth radius planet on a 5-day orbit. That's pretty neat. Another K2 highlight, of course, is that there are planets orbiting bright stars that are well suited for radio velocity follow-up observations. One of the many examples is this system here. This came out quite recently, and this is a K2 planet announced by Andrew Vanderburg just this week. We have one planet on a 1-day period and another planet on a 30-day period. A final example from K2 is that we now know that there are many, many small planets orbiting bright stars. So Andrew's planet is only one example. There was a paper that came out by Ian Crossfield that had a press release this week as well. And the image here is showing a bunch of different K2 fields with the planets announced in that paper highlighted. All of those yellow dots are newly validated planets. Here's their distribution in terms of radius versus orbital period. And you can see all of the blue dots are validated, all of the yellow dots are planet candidates, and all the red ones are false positives. So by using VESPA, which Tim Morton discussed earlier this week, Ian was able to figure out which ones are real and which ones are not. If we look at the distribution of planet sizes, you can see that the majority of them are actually quite small. The advantage of K2, of course, because we're looking at different fields of the sky over time, is that we're able to survey a large number of bright stars. So if you plot, as Ian did, the radii planets versus the J-band magnitude, you'll see that compared to Kepler objects, which are shown in gray, the K2 objects are pushed towards the left, indicating that they orbit brighter stars better suited for follow-up observations. In fact, if you look at the distribution of planets in terms of radius and J-band magnitude and compare how the number of known planets has changed as a result of K2, you can see there's a huge 31% increase here for the number of small planets orbiting relatively bright stars that are good for, say, James Webb observations. There's more K2 science highlights online, and this figure shows a couple of them here. I also want to point out that K2 doesn't just do planets. K2 also does stars and extragalactic and galactic astronomy. Well, knowing that K2 did so well, we'd like to know whether the mission will continue or not. Just like you have to take qualifying exams in graduate school, missions have to go up to the senior review. K2 just did that recently, and it passed with flying colors. Here's K2's report card. It was ranked excellent in multiple categories, and here are some of the choice remarks from K2's instructors. It's cleverly repurposed. It's an ideal example of why NASA keeps missions operating past the prime mission. Exceeded expectations, cutting-edge breakthroughs, and dramatic observations. This is pretty great. I would put this on my fridge if I were Kepler's parents. The end of the story is that K2 has been renewed and does not have to go through the senior review again until the end of the mission. This is wonderful, and it means that all of you can continue working with K2 data. Fast forwarding through our timeline, we've done Kepler and K2. Let's look at Tess. For Tess, I'm showing slides that I borrowed from Zach Berta-Thompson with his permission. He gave a great talk in Davos, and you can find more about Tess online at the mission website. Tess's goal is to try to find planets orbiting bright stars that are well suited for characterization. The project is managed out of MIT and Harvard. And there are many, many institutions involved, a subset of which are listed here. We're going to go through a couple topics with Tess, and the first thing we're going to do is try to explain why we actually need Tess. You're all exoplaneters, so I probably don't need to convince you that we need to find more planets. But let's take a look at what the sky looks like today. This is going to show you a movie where all of the Kepler detections are in blue and all the non-Kepler detections are in gray. We're going to zoom out, and you can see here, these right ascension marks show you which directions you're looking. So this is just collapsing the night sky into the distance dimension. It's a top-down view of the planets we know. If we keep going, we'll see the first planets to appear are planets from designated surveys, particularly looking at bright stars, mostly radio velocity and sometimes ground-based transit surveys. We also start to see this blue spike coming out here, and that's, of course, the Kepler mission. The spikes in different directions are most likely from K2. It's a lot of planets there, and it's pretty impressive to see just how many dots there are on this diagram. But one thing you probably noticed is that this looks really, really asymmetric. We've got all these planets over here, not many planets over here, and for the most part, these guys are pretty far away. If we collapse this down and make a plot of how far the planets are from us versus how big they are, you can see that all the Kepler planets are shoved up over here. They're hundreds of parsecs from us, which means they're difficult targets for things like imaging or for radial velocity observations because their stars are faint, and they're really just not the best candidates for follow-up observations. But that's okay, because Kepler wasn't designed to identify planets for follow-up observations. It was designed to do exoplanet occurrence rates, and it was wonderful for that. In some ways, we can think of the James Webb mission as the future of exoplanets in the near term. In that sense, we need to figure out where we're going to point James Webb, and you could imagine, perhaps, that Tess will serve as the finder scope for James Webb. Tess will do this by identifying planets that are good targets for future atmospheric characterization. How will Tess do this? Well, fundamentally, Tess is a photometer. It's just going to measure the brightnesses of stars. It does that using 4 different cameras, each of which is 10.5 centimeters in diameter. So that's pretty tiny. But it has a huge field of view. It's 24 by 24 degrees. Remember, for context, the whole Kepler mission was looking at about 100 square degrees. So Tess is really going to expand our sky coverage. And I should say, if you want to learn more about the Tess mission, you should also talk with Akshata and Luke, who are here at this meeting and have spent a significant part of their grad school careers working on the Tess mission. Here's a subset that Zach provided showing a 1 degree square field of a Tess detector pixel. So this is what you might expect to see with Tess. If we now zoom out, you can see we're now looking at a full view from one of the CCDs, and there are 4 of these per camera. So we end up with 24 by 24 degrees. It's a huge chunk of the sky. For context, you could fit all of Orion in this view from a single Tess camera. And Tess has 4 of these, which means Tess is going to do a great job covering the sky. We're going to point one of the cameras, at the top one here, up at the ecliptic pole and extend the other ones downward. So as the mission progresses, we'll look at one stripe of the sky, for instance, this region outlined in blue, and then 27 days later, or 1 month, it's like a lunar month, you'll look at the next sector of the sky and keep going. This image here shows Tess starting in the north, but we're actually going to start in the south. At the end of the 2-year baseline mission, this is what the sky coverage will look like. People often talk about Tess as being designed for short period planets because it's only going to look for 27 days. Well, that's partially true. All of these regions here in blue will be observed for 27 days, but Tess is also going to observe other parts of the sky for much longer periods of time. In fact, this region up here is going to be observed for almost a full year because of the overlap between the camera fields. This is wonderful. It means that Tess will be able to detect long period planets that might actually be habitable, particularly planets up here in this kind of dashed region where James Webb will be able to stare continuously. And that's not a coincidence. If you want to know what we'll do with Tess after the 2 years, you should ask Luke for his recommendations. We're now going to take a quick tour of the Tess hardware. These are slides that Zach prepared, and I'm not a hardware expert myself, so if you want to know more, you should ask Ashanta, because she's actually been working on Tess hardware. You can see that Tess is currently under construction. They're building the cameras, and here's a movie showing actual Tess cameras in operation, which is pretty neat. They're assembling CCDs and electronics. They're building lenses. They're characterizing the detectors. There's a baffle to make sure there's no extra light getting into the telescope. And they're working on the antenna. There's a reaction wheel, which is not the same brand used by Kepler, don't worry. There's also been testing of the actual spacecraft assembly. And the solar panels are under construction. So this is great. Tess is happening. We're making great progress for the future. What data will you get from Tess? How will you look for planets in the Tess data? Well, there are 3 main types of data. The first type are these 2-second observations. Those are used on the spacecraft for guiding purposes. They won't be downloaded. Then there are astroseismology targets, where we'll collect data every 20 seconds. There's also going to be a set of targets where we get data every 2 minutes. Those are the prime planet search targets. Those observations will be collected at 2-minute cadence, which for reference is significantly faster than the 30-minute cadence used for Kepler planet search targets. Similarly, 20 seconds is better than the 1-minute cadence used for Kepler short cadence. So we're making great progress in our ability to both detect planetary transits. We'll actually be able to see the morphology of ingress and egress with Tess photometry, which is fantastic, and will reduce degeneracies when fitting planets. In addition to these observations, which are downloaded as postage stamps, just like those used for Kepler and K2, there will also be full-frame images. those are going to be saved every 30 minutes, which is the same pace that Kepler used for long cadence observations. This means that even if your favorite star isn't a planet search target, you could still construct a light curve where you have data points every 30 minutes by reducing the full frame images. This means there's going to be lots of great science done with Tess. Here's Tess's sensitivity. Here we have the noise level in parts per million on the time scale of an hour versus the apparent magnitude of the target and a whole bunch of different noise terms. You want to pay attention to this black curve here, showing you what you would expect to find for a particular star. For reference, we'll expect to see noise levels of, say, 200 parts per million for a 10th magnitude star, and we'll be able to do 1% photometry for a 16th magnitude star. For Kepler, those numbers were supposed to be something like 20 parts per million for a 12th magnitude star. So Tess does not have the same photometric precision as Kepler, but it's looking at brighter targets and more of them. So Tess will still be able to find some very interesting small planets. When does Tess happen? Well, the answer is pretty soon. We're launching on the 20th of December, 2017 on a Falcon 9 rocket, which is fantastic. Here's the timeline for the future of Tess observations. Launch here in 2017, then we'll survey the south and then the north, and then we're going to ask Luke for what to do in the extended mission. The data will all be made public, so 4 months after launch, you'll be able to look up the Tess light curves along with Tess objects of interest, or TOIs. Those are just like the KOIs from the Kepler mission. And the full-frame images will also be available for downlink. If you want to get involved with Tess, you can. There's a guest investigator program, so start writing your proposals now and submit them. If you're in the US, you can even get money to do this, which is always helpful. Going back to the timeline, we've done Kepler, K2, and Tess. At the same time as Tess, we have the Cheops mission, which is an ESA mission. Cheops is fundamentally different from Kepler, K2, and Tess. Those missions survey many stars at the same time, trying to find transiting planets. Cheops does follow-up observations of a single star at a time. The way this works is that it's going to be characterizing exoplanets as a satellite. Here's the goals of the mission. It's mostly going to focus on the brighter stars detected by, say, Tess, to host transiting planets, and it'll operate for 3.5 years from an Earth-based orbit. So it's going to be sun synchronous, which means you have to be careful about when you plan your observations because you can't always look at all the stars all the time. Cheops is bigger than Tess. It's 33 centimeters in aperture, which means it has 9 times the collecting area. So you'll be able to get higher precision transit observations that'll help you refine the radii of the planets you detected with Tess. It's also going to be great for looking at radial velocity detected planets to see whether they transit, assuming you have some rough idea of when that transit might occur. In terms of precision, we'll get down to 20 parts per million in 6 hours on V magnitude of 6 to 9 stars. That's great. Those are Kepler-like numbers, but of course for brighter stars. Cheops is also under construction, so here's an image here showing the engineering test model in a lab in Europe. Going back to the timeline, we've done Cheops. After Cheops in 2018, we have James Webb, which we've heard about in other presentations. And then in 2024, we'll have Plato. This mission is pretty incredible, but it's so far in the future that many of the details are still being worked out. So there's a good chance things could change between today and 2024. Plato stands for Planetary Transits and Oscillations of Stars. It's a much better acronym than Cheops if you paid attention to which letters were capitalized before. Plato is supposed to last for about 6 years, and it's going to be out all the way at L2. So we don't need to worry so much about the Earth and the Sun and the Moon getting in the way of our observations with Plato. They're going to do an interesting strategy with the observations. They're actually going to have a whole bunch of tiny little telescopes together. Each of these little telescopes has an aperture of 12 centimeters, so kind of Tess-like, but together they have a full field of view of over 2,000 square degrees. That's enormous. It's like putting something like hat pie in space. The way Plato will operate is that they'll have 2 strategies. One of those strategies is going to be to stare at a region of the sky for a long period of time, kind of like Kepler. The other strategy is going to be to stare at regions for shorter periods of time, a couple months or so. And that will be more like a K2 phase of observation. Within each of those fields, they'll look at 150,000 stars, and by the end of the full mission, they'll have surveyed 1 million stars, which is similar to the number of stars surveyed by Tess. But Plato will have higher precision than Tess. Here's a map of where those pointings could be. This is still under deliberation. Right now, you can see that one of these pointings for the long stare, which would last for about 2 years, is centered around the Kepler field. So the 2 things you should take away from this is that, yes, with Plato, you'll have the opportunity to see Kepler planets again. But remember, Plato's not really doing V of 15 stars. It's doing brighter stars. And the other thing to take away from this is that the Plato field is enormous compared to the Kepler field. How will Plato actually collect these observations? You saw that array of all those 12-centimeter telescopes. There are two types of those. Some of those are what they call normal cameras. Those will be observing stars with a cadence of 25 seconds. So once again, we're faster than Tess was, in the same way that Tess is faster than Kepler in K2. And the other set of cameras, probably two cameras, will be what they call fast cameras. And those will observe stars every 2.5 seconds. Because they have shorter integration times, those cameras can be used for brighter stars. So you could actually search for planets around stars that are fourth magnitude, which means you could take your family out in the backyard and actually show them a star that has a planet around it, and you would know that because of the Plato mission. Looking at the end result of the Plato mission, if you ask yourself, is there a planet in the Plato data, the answer is probably going to be yes. This figure here is showing the number of planets they expect to detect versus orbital period, which are the top numbers, or semi-major axis, which are the bottom numbers. This is a little bit of a complicated figure because they've done some black magic behind the scenes. You would expect naively to have much higher spikes for Tess and Kepler on the bottom here, where Tess is shown in red and Kepler is shown in blue. What they've done here is that they're plotting only the planets for which they think they'll be fully characterized, which means they have a host star that's 11th magnitude or brighter, which means they could then go and measure the mass of the planet. This will require a significant investment of ground-based radial velocity observations. So Plato talks a lot about measuring the masses of planets, but remember, that's not going to be done with the spacecraft. You also need to do the mass measurements from the ground, or perhaps with the data if you have TTVs. That said, if you look at all of these green bars here, you're really going to get a whole truckload of characterizable planets from the Plato mission. So you'll have plenty of projects for your own graduate students to work on in the future. Wrapping up, here's our timeline again. We started off with the Kepler mission. We saw K2 is really discovering many, many new planets around different parts of the sky. We learned about Tess and Cheops. We skipped over James Webb and ended up with Plato. I think the main things to take from this picture are that, one, Kepler told us that planets are common. It was primarily an exoplanet statistics mission that laid the groundwork for all of these future observations. Kepler looked at a single set of stars for a long period of time. K2, knowing from Kepler that stars were common, and also having the issue that it could only point in certain directions, instead looked at different fields. And within each of those fields, found more planets around slightly brighter stars than the main Kepler mission. Tess is going to take that one step farther by looking at the entire sky and finding planets around even brighter stars. With Plato, we're going to continue the trend towards brighter and brighter stars, but we're going to go back a little bit to the Kepler strategy of staring for longer. That's the roadmap for future transit observations in the next 8 years or so, and I'm curious to see what changes we have as we go forward on to the 2040s, whether we have a Habex-type mission or a LIVOIR-type mission. I'm going to conclude by showing you another video from Zach Berta-Thompson. And this time, in addition to the Kepler planets and the non-Kepler planets, you'll see a whole bunch of red dots. Those are the predicted detections from the Tess mission. And I'll confess that when I first saw this, I was quite stunned to see how many of them were so close to us here on Earth. Here we go. It's a lot of planets. Right. That's the yield of the Tess mission. And many of those targets might actually be later observed by Webb and Cheops. And I'm curious to see what you'll find out when you study those planets in more detail. Thank you very much.
Which of the upcoming missions will have this ability to?
Okay, so your question was, in contrast to the Kepler mission with K2, we've seen confirmations of planets with a single transit. Which future missions will do the same? I think it's challenging to confirm things with a single transit. There have been examples with K2 where you found a single transit, you thought you knew when that planet was going to transit, and then people observed it from space, and they thought they detected it, but then we got Spitzer observations and realized that the actual ephemeris was incorrect. So it's going to be a risky game. But if you have Tess observations, you have 2-minute cadence observations, which means you have a better handle on the exact transit duration, and you can therefore better predict the orbital period of the planet. So you would probably then take Cheops and see if you can find a transit. Or better yet, you'd use a radial velocity ground-based telescope to figure out what the orbital period of the system was and then use Cheops. So you could do a validation like what Tim Morton described using VESPA, but if you don't know the orbital period, it's difficult to tell which priors you should use. Ah, that's a good point. The continuous viewing zone for Tess is rather small, and Tess's telescopes are small, so the star having an advantage of having a larger section of the sky where you can find more bright stars doesn't necessarily apply within the region where you have continuous coverage. I think the key there is that you still get a year worth of coverage, and that hasn't been previously studied by Kepler, so there's still low-hanging fruit there left to pick off. For looking at the yields, I think there are about a dozen or so planets that are small, meaning 2 or 3 radii or below, that are within receiving installations between that received by the Earth and Venus and Mars. Many of those are located in that part of the sky, and they primarily orbit M and K dwarfs.
Can you just explain why exactly?
Sure. Why is Tess the People's Telescope? Well, at the risk of sounding like a communist, I think Tess in some ways really does go back to the community, because we now have the K2 era where many people have homegrown planet detection pipelines. So even though the Tess team is going to be releasing a list of toys, Tess objects of interest, many people are planning to just run the photometry through their own pipelines and find their own planets. The other way in which Tess will be the People's Telescope is that there's going to be a follow-up effort, and Tess is going to be finding planets across the entire sky. Kepler follow-up was a huge logistical challenge, and people like Dave Ciardi lost years off their lives by spending many, many nights sleepless at telescopes. Tess is going to be a whole different game in terms of how many telescopes are needed to follow up these planets. The pixels for Tess are 20 arcseconds wide. So within a particular pixel, you might have a transit event and have very little understanding of which of those stars is causing the transit event until you go to the telescope. And the odds that your transit event is diluted by another star are also higher than for the Kepler mission. You're helped a bit by the fact that your stars are brighter, but there's still going to be a tremendous amount of ground-based observation required.
What would you say the role of ground-based surveys is now Tess and all this kind of stuff?
What is the role of ground-based surveys with Tess coming up? One of the things I've learned by talking to people who study planet formation and by people like Angie Wolfgang is that if you really don't know the mass of the planet as well, you don't know the system as well, and it's hard to say much about how that planetary system evolved. So with ground-based surveys, we can get masses, which I think is tremendously important. We also need adaptive optics observations to tell which of these stars harbor planets, which of these stars are single. Gaia will help us figure out which of the stars are single. But there's still so much we don't know about these stars. And that actually boils down to things as simple as how big are they, how hot are they, and how massive are they?
I was thinking more like ground-based photometric surveys looking for additional transits.
Yes, okay, so ground-based surveys looking for additional transits will also be important because many of the test planets will transit only a couple times during the 27-day period. So you want to re-observe those to make sure that if you saw 2 transits, you saw the same planet transit once instead of two planets each transiting a single time. And you would like to know whether you're also finding systems of closely packed planets where maybe you see the inner planets transit but not the outer ones.
If you see it in that star in the ground.
That's an excellent point. Scott pointed out that you can actually use the archival ground-based data from large transit surveys to pre-cover transits that you detect with Tess, and that will help you figure out the orbital period. And there are a couple graduate students at Princeton that are currently working on that, combining the Tess simulated full-frame images with HAT data, and they have some cool results. That's a great point. Chaz pointed out that Plato is also going to give us astroseismology, so we'll not only know the size of the planets, we'll know the ages of the stars, which will help us get tighter error bars on the radii and masses of the planets and actually figure out how long they've lived there and what type of insolation environments they might have experienced in the past. And by fully characterizable on that bar chart showing all those green bars, that included both having a bright star and also having an astroseismically constrained star.